During the late Devonian period, the oceans were highly competitive environments dominated by placoderms, the earliest jawed vertebrates. Typically, these early arthrodire fish featured robust U-shaped jaws. Their biomechanics were optimized to withstand massive physical stress, snapping shut rapidly to crush the hard shells of their prey. But the fossil record for Alienacanthus malkovskii breaks that rule. You can see here how its lower jaw extends far past its armored body. Specifically, the inferognathal, the lower jawbone, is exactly twice the length of the upper skull. This precise 1:2 ratio means the standard model of placoderm crushing mechanics no longer applies. To understand how this animal fed, we have to examine an entirely different predatory strategy. In biology, evolutionary modularity is the ability of specific anatomical components within a system to evolve independently from the rest of the organism. Alienacanthus represents the earliest proof of extreme upper and lower jaw decoupling in the vertebrate timeline, separated by 400 million years from any modern equivalent. To prove exactly how this elongated jaw functioned in the water, we have to reverse engineer its mechanics. That requires breaking down its jaw occlusion, tooth geometry, and microscopic bone histology. Understanding this specific anatomy shows that highly specialized asymmetrical biological engineering was active in the earliest stages of jawed vertebrate evolution. In a standard arthrodire jaw, contact happens both at the front and along the sides, forming a complete U-shaped seal when the mouth closes. Alienacanthus lacks this anterior contact entirely. Its lower jaw slides medially inside the upper jaws, relying exclusively on lateral occlusion. This slide is accommodated by the flattened anterior and posterior superognathals. The dorsal processes in this joint align perfectly parallel to the shearing surface, rather than at a standard 90-degree angle. Because of this lateral-only, parallel axis movement, Alienacanthus was mechanically incapable of biting off chunks of prey. Any capture had to be swallowed whole. Looking at the gnathal plates, the teeth lining the jaw are severely recurved, hooking backward toward the throat. This is known as xiphodont tooth morphology. It is a biological design optimized for unidirectional trapping rather than cutting or tearing. When these jaws close on a fast-moving, soft-bodied animal suspended in a fluid, the angles of the teeth naturally force the prey deeper toward the esophagus the more it struggles. This exact trap mechanism independently evolved in completely unrelated semi-aquatic predators millions of years later, including Triassic cetaceuchians. By sacrificing vertical bite force, Alienacanthus transformed its skull into an inescapable cage, mechanically adapted for securing prey in open water. That trap alone doesn't explain the full anatomy. We must account for the massive section of the lower jaw protruding far past the upper skull. A critical detail is that functional teeth continue all the way down this exposed, forward-reaching section of the bone. While modern sawfish use long rostra packed with sensory organs for electroresection, cross-sections of this fossil lack the nerve canals required for that function. This leaves a kinetic explanation. This massively elongated, toothed cantilever was deployed as a physical weapon to slash directly into schools of small fish. The predatory sequence began with a high-speed strike to injure and disorient prey in the water column, before guiding them into the posterior trap. This extreme elongation functioned as a hydrodynamic halberd, extending the predator's lethal range well beyond its bite radius. A cantilever this long presents a structural paradox. A solid bone is too heavy to swing quickly, while a thin bone snaps upon striking. This histological cross-section reveals how the internal architecture solved the problem. The interior consists of highly porous trabecular bone. This sponge-like structure drastically reduced mass while maintaining rigidity against lateral forces, meeting at a tight external margin with the tooth-bearing bone. This slide shows the concentric bone cell lacunae. Unlike its relatives, Alienacanthus added new teeth strictly in a posterior direction as it grew, maintaining the hydrodynamic profile of the front blade. The microanatomy reveals an optimized weapon, dense on the outside to anchor teeth and absorb impacts, but light on the inside to allow lightning-fast strikes. This degree of developmental decoupling between the upper and lower jaws is extraordinarily rare in the fossil record. We see a similar dissociation in jaw lengths today in modern ray-finned halfbeaks, but Alienacanthus predates these modern analogs by hundreds of millions of years, establishing it as the pioneer of this extreme morphological niche. The architecture of the vertebrate skull did not require millions of years of gradual tweaking to experiment with extreme asymmetry. Highly specialized and lethal innovation was present in our evolutionary blueprint from the very earliest stages of vertebrate evolution.